Okay, thanks everybody for coming to this centennial session. This is the second year that we've had this Visions of Future Innovations across space physics and aeronomy. It was really successful last year, and I hope we have a lively discussion again this year. One quick note before we get started, Dave McKenzie is not going to be here for the second talk, so we'll have 15 or 20 minutes of silence in honor of Dave. But our first talk today is Sarah Gibson. Should we get, she's going to speak about Sunny Side Up, the promise of future solar polar missions.
Okay, thank you. Let's see what we got here. And the advanced slide is just the arrow here, I assume?
Sure.
Okay.
I'm going to try.
All right, thank you very much. Yes, I will be talking about what kind of science would be enabled by having a mission that goes to the sun's poles to get the sunny side up view where you're looking down on the ecliptic plane. And you're able, no, it doesn't seem to be. Return?
Oh, is it only this one?
All right, let me just stand. Yeah, I'll take it. All right, so you see my little satellite going above the poles. Now, this talk is basically a workshop report because we had a workshop at AGU in September called Polar Perspectives, which looked at the science that could be achieved, again, from the solar poles, the solar interior, the global connections in the corona, the solar wind and heliosphere, space weather, and also we had a session on the technologies that need to be developed or are existing to enable these missions and mission concepts. And our invited speakers include these people here, and a lot of what I'm going to show today will be drawing from the presentations that they gave. And all of the presentations at this workshop are available online if you search on Polar Perspectives AGU. And in fact, they're all available on YouTube, and there's some great lectures there, so I encourage you to check them out. So today, I don't have time to talk about everything we discussed at the workshop, so I'm going to focus on two very top-level outstanding questions of heliophysics that are uniquely enabled by a polar perspective. The first one is, how do solar surface and subsurface flows vary at high latitudes? And the second is, what is the total open magnetic flux in polar coronal holes? And what I will do is talk about what do we know about these questions so far, what don't we know, why does it matter, and how would a high latitude vantage help? And I'll conclude by talking about the sunny side up view in general, and space weather in particular. So let's start with that first question. How do the solar surface and subsurface global flows vary at high latitudes? Well, what do we know? We know quite a lot about the differential rotation of the sun, inside and at the surface of the sun. We've known since we've been observing sunspots that, for example, that the equator rotates faster than the poles. And with the advent of helioseismology, we're able to take that in deeper. And there we see that red is fast, blue is slow, continues as you go in until you reach this very important shear layer between the convection zone and the solar radiative core known as the tachocline. There's another shear layer as well near the surface. And we note that the flows are not constant on cylinders, which is what one would expect from a simple model. And this implies that there must be a distribution of angular momentum by convection that has to somehow play a role to get this observed profile. Those are east-west flows, so flows in this direction. What do we know about north-south flows? These are weaker, harder to observe, but we can measure them, and this is showing the meridional circulation, where now red is going up and blue is going down, so you see that this is a flow that is poleward in both hemispheres to first order. So this is what we know. Well, what don't we know? Well, again, using helioseismology, we can look at the meridional circulation patterns as a function of depth. And here we reach quite a lot of uncertainty. This collection is a collection of studies giving differential rotation, where again, red is poleward and blue is equatorward, 5 different cases using different data sets, different times in the solar cycle, and getting different results. Now, there may be changes over the course of the solar cycle, but there's really a lot of uncertainty and no consensus about what the structure is of the meridional circulation below the solar surface, and in particular at high latitudes. In fact, it was pointed out at our workshop that if you look just near the equator and near the surface, they're not that far off, they're not that different, but as you look up towards the poles, they're real discrepancies, differences about how many cells there are, whether there's a return flow going back down to the equator, etc. Well, why does this matter? First of all, in a classic Babcock-Layton dynamo model, in which basically toroidal magnetic flux is converted into poloidal magnetic flux over the course of the solar cycle, and it's converted by flux emergence, and then meridional circulation plays a crucial role of moving the flux to the poles. And in that case, the circulation is really setting the clock for the flux transport dynamo. And the return flow is assumed, it's required. If there are, for example, extra high latitude cells at then this can speed up and change the cycle period. And for example, it was used to explain the extended solar cycle minimum that we had recently. For global convective models, on the other hand, the meridional circulation and differential rotation are not the inputs to the model, but rather the outputs, because these models solve the momentum equations. And in this case, however, in these models, however, there are assumptions that have to be made, in particular about the dispersion of energies, magnetic, thermal, mechanical. And depending on the assumptions that are made, you can get different output, differential rotation, and meridional circulation, which are very tightly coupled. And for example, a single circulation cell is associated with an anti-solar differential rotation, where the poles are actually going slower than the equator, whereas multiple cells generally makes it easier for the convective processes to redistribute the angular momentum and end up with the solar-like differential rotation. So again, it's significant. Here, it is not an input, but it is a check and a constraint on these global circulation, on these global convective simulations. So how would a high latitude vantage help us? Well, first of all, if we could directly measure from the polar vantage Doppler observations, if we could do feature tracking, and if we could do local helioseismology, we could learn about the subsurface flows, and we could avoid and address very critical things that really limit us from the ecliptic. For example, foreshortening, center-to-limb effects, and in the helioseismology, there's how do you basically deal or interpret the horizontal component of the oscillations, which is what you're mostly observing from the ecliptic view. And this would allow us to investigate exactly what I'm talking about, the meridional circulation as a function of latitude and depth. We could also look at things, for example, the differential rotation profile as we get close to the sun. Is there evidence for a polar spin up or a spin down that we haven't observed? We could look at the nature of convection at the poles and compare it to convection and supergranulation, for example, at low latitudes. So there's a lot of discovery space there. And given multi-angle views, if we had simultaneous sustained polar vantage and ecliptic vantage, we might be able to probe even deeper than we can now using longer ray paths for helioseismology. So there's a lot that could be learned. Let me turn to the second question. What is the total open magnetic flux in polar coronal holes? Well, what do we know? The polar magnetic field, we've gotten some recent observations from Heliospheric, which really have allowed us to peer closer and at higher resolution than we ever have. And in particular, these indicate that the polar magnetic field has patches of strong kilogauss field. And when we combine that with observations, synoptic observations, in this case SOLAS, we get a pretty good model of the global sun. In this case, we're looking at a Carrington map, latitude and longitude, and we're seeing the magnetic field, longitude and magnetic field, white and black, positive and negative. Well, what don't we know? Well, the problem is we really don't know just how peaked and how strong the polar magnetic field is. In this case, you're looking at 4 different observatories, giving you 4 different magnetographs, Carrington maps, and I think we've got Wilcox Observatory, Gong, SOLAS, and probably HMI. And the Earths are on the same color scale, and so you can see that there's quite a significant difference in terms of what they're saying the polar magnetic field strength is. And when we talk about polar coronal holes, we also have uncertainties because we're looking from the ecliptic. We have projection effects, we have evolutionary effects because we're looking at just 1/2 of the polar coronal hole at any one time, unless we have stereo, which might give us some more information. But there's basically a scale height, there's a wall of plasma that blocks what we can see in the polar coronal holes. And so the question of are there fundamental differences between polar and low latitude coronal holes really is an open question. What don't we know? What else don't we know? Sorry. This was a study done by Linker et al., where they took as many different, a whole variety of models and different boundary conditions and made predictions about the open magnetic flux. And they also looked at extreme ultraviolet to get a sense of the polar coronal holes in order to get the very best assessment of how much magnetic flux was open to the heliosphere. And what they found was that systematically, so for all of the models, so this is even for all those different cases of boundary conditions, they all systematically underpredicted the amount of open magnetic flux in the heliosphere when you compare it to observations in the solar wind, which means there's two possibilities. Either your assessment of where the open flux originates, so where the coronal holes are, for example, or other open flux regions is not right, or that your photospheric magnetic fields may be wrong, in particular at the poles. So why does it matter? Well, the polar magnetic field, the amount of open flux, this is what we're talking about here, is essentially a boundary condition on the heliosphere. So if we're trying to understand the heliosphere as a united Sun-Earth system, we have to get this right. It's fundamental. How would a high latitude vantage help? Well, first of all, it would let us look right down on the strength and distribution of magnetic field at the poles. And Pete Riley gave a very nice example of this, where he made a model with a sort of a top knot of strong magnetic field, enough to solve this heliospheric flux problem, mystery. And he showed that if you were to observe it from the ecliptic, you get something very much like we observe now. The 7.25 degree tilt over the year, which is essentially how we know that it's a strongly peaked function because the polar fields increase as we start to look right down at them, would help a little. Solar orbiter might be enough depending on how concentrated it was, but if we were to be able to actually look right down the barrel of this structure at the poles, we would be able to resolve this question once and for all. In terms of the EUV, this is a nice movie that Scott McIntosh put together. He took advantage of when stereo was observing both sides of the sun, so he could make a synchronic EUV map and unwrap it around a sphere. So you are seeing essentially all longitudes at the same time, which is one of the huge advantages of looking from a polar perspective. But it's very, very smeary because of the aforementioned projection effects that we're looking basically at a very, very, through a lot of plasma. So a polar perspective would let you resolve that polar coronal hole in a way that's just not possible with ecliptic view observations. So let me conclude by talking a little bit about the sunny side up view and its implications for space weather. Vic Pizzo gave a very nice talk, I can encourage you to watch it, where he talked about how even with stereo views, near ecliptic views only can be ambiguous. And he showed what he called a coronal head fake. And essentially what's happening is when you're looking along the ecliptic, you have quite a lot of line of sight ambiguity because you don't know what's in the foreground, you don't know what's in the background, you're weighted towards the plane of the sky. And in this case, there was a CME that looked like it was going down into the, it was going down into the right there. And that was the trajectory that was assumed. But in fact, it was a deflection of ecliptic material in that direction, and the trajectory of the CME was something completely different. And so we can't see the full extent of global interactions when we're looking from the ecliptic point of view. Chip Manchester gave an example of some synthetic modeling of CMEs, and he's showing this is the ecliptic view, and this is the North Polar view. And again, from the North Polar view or South Polar view, you have minimal line of sight confusion because you're looking down on the structure in a thin, think of that egg picture at the beginning, you're looking at the egg white, right? Instead of along the egg white on a spatula held in front of your face or something like that, which would be very confusing. And if we have both, again, you can also get information about the 3D morphology and the trajectory better than you could otherwise. And so here we are. This is that fried egg view in an NLO model from the CCMC. And you can see the sun at the front, in the middle, and all the planets around it. You can see a CME going out like that. You can see the Parker spiral and co-rotating interaction regions forming. This view is showing you the longitudinal structure in a way we've never observed it before. And you can see, probably most exciting from a space weather point of view, is you will see all of the Earth and planet directed transients all of the time because you're looking down on them, and they tend to be focused on the ecliptic. So the last slide I want to show is, of course, what is the discovery space? This is a picture of Jupiter at its poles, and nobody expected this kind of structure. And I imagine that when we look down on the magnetic field and the flows and the EUV in particular at the poles, we will see something spectacular. So these are all very strong motivations, and I do want to finish with one last comment, which is that this entire line of research that I'm working on right now was inspired by one of the co-authors on this talk, who is Michael Thompson, and who passed away this fall, and so he is greatly missed and was a real inspiration to this. Thank you.
Any questions? Any questions?
Jim?
There was a recent news article about an observation of reconstructing
Yeah.
There was a recent, is it on? There was a recent news article about reconstruction using, I can't remember the name of the instrument, the one in the Belgian instrument.
Oh, right, yeah.
Proba 2. Can you comment on that?
Yeah, that's great. I mean, there's, and using what we have from the ecliptic view to get a sense of what's going on in the poles, they are doing some very careful, very good work to try to do that, and that will give us an insight. But of course, I think they'd be the first to admit it. You can't, it's not going to replace what you could see if you really flew over the poles.
Jim Connell?
Of course, I feel constrained to mention that there has been one solar polar mission, Ulysses, which did not have an imager, though the original US mission second satellite was supposed to. I wonder at the same time, you've talked about flux over the poles. I would have thought that the magnetometer data from Ulysses would have been valuable for some of those studies.
Absolutely. In fact, it was crucial for me to make the statements that I've made. I mean, when Ulysses went over the pole, it revolutionized our understanding of the heliospheric structure because it saw, for example, that the open magnetic flux was essentially uniform in the open regions from pole to equator. And so everything I just said about the heliospheric flux is using the interpretation we gained by going to the poles with Ulysses. So it was a paradigm shift, and I think imaging from the poles will be another paradigm shift.
Ed, do you want to use the microphone?
So I think one of the aspects that needs to be done in addition to sort of the instrumentation hardware side is really to have a push to convince the community that when you have the new polar data sets, that the tools for analyzing them with internal convection models, with helioseismology constraints on those models, including the magnetic fields, that all of that is kind of in place. I mean, there's obviously time to do it because there is no mission, but I think we should talk a bit about the development need on the simulation side and the forward modeling side from the interior to helioseismology observations, because I think there's a disconnect there that still exists and is troublesome in the, if you're anticipating deriving an entirely new data set that we haven't seen yet.
Yeah, that's a very good point. I will point out that for the first discovery, there would be a tremendous amount that could be done by sending our bog standard coronagraph, Doppler magnetograph, UV imagers to the poles, data that we're all incredibly familiar with and know how to analyze, but getting that different vantage would answer questions. So the data will be quite familiar in that sense. However, your point is well taken in that in how you incorporate them and use them in models, it's different than anything we've really undertaken, and we need to think that through.
Okay, great. Let's thank Sarah. She's got to go give another talk. So we'll have about a 10-minute break, and then our next talk will be by Craig DeForest at 10:50.
Just wanted, just in case.
Okay, fair enough.
Yeah, how are you doing?
Hey, how are you?
All right.
You have a short commute now, isn't it?
I do, yes. Yes.
Probably changed your whole life, right?
It's all right. It's about an hour a day. So that's nice. Yeah.
Working with a team project.
No kidding. Ah.
Yeah, it's
Right. Yeah. You're right, exactly. Yeah. So you working with him through NSF or through Astor? Okay. That's cool. So you're still in San Antonio? Yeah, I remember. Yeah. Excellent. To San Antonio? APL? Oh, okay.
Yeah, if you want to go, just say an hour.
Okay. All right. Alan starts from course, yes. I'm trying to think. Is that his SWRI address?
Yeah.
Okay, all right. Okay. I might.
You're nearby.
Right, exactly. I saw him a year ago, dinner with him at the Space Weather. He was a guest speaker. Yeah. Oh, he knows who I am.
Yeah, for people who are
That is excellent. Are you going to the mission or something?
No,
I'm not either. I just don't want to. Yeah, it is.
yeah,
I've got. I'm not sure. Speaker writing room. We're just. I have a talk at 4.
right after this.
Yeah, that's what I'm thinking. That's what I'm editing the charts right now as well. That's good. That's good. It's nice to have like one room.
Okay. That's as far as it'll go. No kidding. Okay. All right. Right.
That's a good point. Thank you for bringing that
Great snacks.
Thanks, Burger.
It must be huge. It's taking forever. Craig usually has a lot of movies. So, Craig, and then Kilo is on PC. Ready? And after that, it's Alessandro. Robin Millen, right? That's what I say. That's how I would say it if I was her. Jonathan?
How's it going, guys? Yeah, we've met before. We had the Thanksgiving together. How was the flight over? You came on Saturday. Yeah. Yeah. Sorry, this is not the environment in which to have a conversation. These microphones are on. We will talk.
Carrie, you have no secrets.
None that you know of, and let's keep it that way. Highly unlikely. It's kind of late, and Aleda told me I didn't have to be there to honor her. Well, somebody from Team Higginson had better show up. I carry the loss. It's not Team Higginson. She's getting the scarf from the torn. She has to. But we should continue. We should hang out. You guys will be on we'll work something out. It's good to see you. Sure, why not, Greg?
Hey, thank you for that very kind meeting. Absolutely. I have to open it up for possible partnership, but I can do it. Just well, because you know I need some meeting. Yes. Yeah. Yeah, that's right. If you happen to start a mini
Okay. All right, if folks would take their seats, we'll get started again. Okay, our next talk is by Craig DeForest. What are you going to talk about? Closing the gap between the sun and the heliosphere.
Ah, there we go. Closing the gap between the sun and the heliosphere. So, whoa. This slide opens with some recent data from the 90s. So that's, I guess, 2010 for the ACE data. This is LASCO. Actually, this is more recent than the 90s, sorry. LASCO on the left and ACE data on the right. Ever since I've been in this field, we've really said there's a sun-Earth connection, or we're all part of one system. People who study space physics and people who study the sun. But in fact, the communities have really diverged. And we're seeing that now as the two communities merge, as technology changes. What's happened is people who study the corona are limited to remote sensing, largely. with some exceptions that you'll learn about later in the week, because there are several solar probe sessions. People who study the solar wind have until recently been limited to a different technology, to in situ sampling of that wind. And so the jargon, the style of thinking, and in fact the physical part of the system being studied has really been wildly different. And we're at a very exciting time right now when the technology of imaging has expanded out from the sun to where we can image the solar wind directly, and the technology of in situ sampling in the form of Parker Solar Probe has advanced enough that we can now sample the corona directly, and we're in fact about to do just that. So I'm going to talk about some of the unification science that needs to be done and what the next step is beyond and to augment Parker Solar Probe. So this is, I think many of you have seen this image before. This is just sort of demonstrating that the sun and the heliosphere are in fact a connected system. This is one of the results to come out of the stereo mission, Stereo SECI. SECI has a large number of different cameras that are all meant to work together to build up a mosaic of the heliosphere as a unit, and this movie sort of demonstrates that, where you can see a CME leave the sun, and then it's going through a distorted coordinate system so you can keep it all in the field of view, but eventually it impacts the Earth, and you can see the solar wind density change as it impacts. So we need to be thinking not just at the top level about this being a unified system, but also in terms of our analysis and how we approach the next scientific problems. We have two large bodies of work that have been done that need to be merged. Talking about, this is sort of, in some ways, the apotheosis of the in situ approach. This is a plot that we've all seen many times from Ulysses, sort of mapping the polar high-speed wind and the various kinds of solar wind as Ulysses wrapped around the sun in a polar orbit. This plot took 4.5 years to make, 4 years, something like that, whatever the orbital period was, and yet it is the only glimpse that we've had really into the solar wind over the poles, and that sort of ties into what Sarah was just talking about. But it leaves a lot of questions open. Why is there so much variation down around the equatorial belt? What is the source of the slow, or even, for that matter, the high-speed solar wind? This is understanding the sun from looking at the solar wind is a wonderful pastime. Lots of us do it. On the other hand, there's a missing link, this sort of gap at the outer corona, or even the inner corona in some cases, where we have to sort of extrapolate inward from the in situ results into the sun, or extrapolate outward from the sun into the solar wind. So stereo really gave us the first glimpses of the shift from the corona to the solar wind. So if you look at this montage is actually in real focal plane coordinates. On the right you have core 2 images, so coronagraph images going out to 15 solar radii, and on the left you have background subtracted high 1 images. And you can see that the character, I don't know if I have do I have a mouse or a pointer or something? Yeah, here we go. Here's a pointer. That'll work. Thank you. So the character of the structures that you're seeing sort of changes. In here it's much more radial, these things that I'm calling striae, that sort of encompasses streamers, pseudo-streamers, plumes, all these radial things come out. Over here they're less prominent, and there's sort of more poofy stuff, if you will. And is this a fundamental change? Well, we know from theory that beta roughly 1, not equals 1, and the Alfvén surface, which I'll come back to, are sort of in this vicinity. But unfortunately, and this is kind of Murphy's law, they always land right around at the boundary between your instruments. So what's the difference here between what's here and here? Is it instrumental or is it real? And we've sort of got some hints about that, but the next step is really to have an instrument that can bridge this gap. So we think the solar wind, I'm just going to move through some topics here quickly so we don't run out of time. There are lots of signs that the solar wind is turbulent. You can see, these are some of my favorite touchstone results, but there are lots more in the literature. There's a huge literature on solar wind turbulence. We see from kinetic scales, from in situ sampling, that there's a dissipation range, dissipating turbulent energy in the solar wind near the Earth. In the middle, you can see this is a result that is, again, very recent from Heather Elliott, that the solar wind is being processed as it makes its way across the solar system. And in the upper right is another recent result that we can actually watch how comet tails break up and use them as test particles to trace turbulent eddies. There's lots of signs that the solar wind is turbulent. Where does the turbulence come from? What's driving it? What are the instabilities? Well, there's a huge literature on this, but it's very hard to measure this directly without either a swarm of samplers or an imager. So looking at the corona, again out to about 30 solar radii in LASCO, you see striae go out. They do not appear turbulent in the same way that a hydrodynamic flow appears turbulent. That's because the large-scale instabilities are suppressed by the curvature force of the magnetic field. That's very much like why you can pick up water with a straw. The surface tension suppresses the Rayleigh-Taylor instability. But when you get farther out, this is the same field of view or same scale. You can see the original LASCO field there. When you get a little farther out, you can see the top of the striae. Again, with highly processed stereo data, we can see that the striae actually sort of come to an end at around 40 or 50 solar radii, and this flocculation, this sort of very puffy field kind of fades in. This is about all that you can do with stereo, but this is very tantalizing because we can see hints that in fact these striae are breaking up and becoming slow solar wind turbulence. But we can't prove it with these data. We can't actually identify the mechanism. We can't see whether it's really happening. All we can really see is that there's some kind of breakup happening. And this is really pushing these data to about the limit. So the other thing to see is that there is stuff coming out, little puffs of material that come from the sun. What's the balance between turbulence and intermittent release? This is an old question. Is solar wind variability from the sun, or is it from the solar wind itself? Well, we're on the verge of being able to tell the answer to that question, but neither solar probe nor any of our current imaging instruments is really up to that task, because solar probe can only sample what it flies through, and we'll get some inroads into it, but to nail that, we really need global cross-scale imaging. The Alphane surface has been something I've been pounding podia about for a while now. This is the outer boundary of the corona, the dynamical outer boundary. There are a number of ideas about where it is. These are simulations from Cohen that I particularly like. It's important partly because it controls the amount of open flux coming from the sun, which is also the inner boundary of the interplanetary magnetic field. And yet we don't have any direct way of measuring it except for images. With solar probe, we can sample pieces of it that get flown through, but we cannot see the global shape of it, and we know that affects the solar wind in the solar system. We've gone looking for it with Core 2, and we found that there's inbound stuff in the corona at all visible altitudes with Core 2, so up to 15 solar radii, much farther than we thought we would find it, but there it is. It turns out there's a reason for that. The corona is much more complex than we've all thought. It turns out every coronagraph flown to date has been noise limited. The effective resolution of a coronagraph is determined not by the pixel size of the optics, but to date it has been largely determined by the noise floor. Eventually, small enough features don't rise above the noise floor and you can't see them, and that sets your resolution. So when we process Core 2 data to reduce noise as much as possible, we see a much more structured corona. If we zoom in here, you can see that these are those little pieces on the last slide. There's structure all the way down to the finest scales you can see, to about 10 megameters across. The density spectrum is 1 over F, as one might expect. It's really exciting, and that 1 over F spectrum goes right down to the optical limits of Core 2, which coincidentally are at the granular scale projected out to the corona. So once again, the really interesting stuff you'd really like to see is right at the limit of what the instrument can do. Dang. So we'd really like to go a little bit deeper. Looking at the photometry, these are cuts through the corona. You can see the photometric brightness variations here. This is without and with unsharp masking to get rid of the streamer. What this tells you is that the electron density varies by a factor of 10 on very small scales. What that in turn means is that there is no Alphane surface. There's no Alphane surface. The reason is long wavelength waves see a different plasma than short wavelength waves. And so short wavelength alphane waves can get into the corona even after they're outside the formal alphane surface. It's frequency dependent. And that means there's this alphane zone of really weird physics where some aspects of the corona are connected to the sun still, and some aspects are really separated as solar wind. This is an area that Solar Probe will fly through, and it will make the first exploration of this wholly new part of the heliosphere. Sorry, you have another eye?
Okay, but you got like 2 minutes.
Okay, so wrapping up. Not a steady flow, but a riotous torrent. Looking in the time domain, if we unsharp mask this movie in time, you can see that the entire corona is full of ejecta at all scales all the time. And we can't show exactly how much of the material is in these ejecta, but we can show that it's consistent with 100%. I'm going to say that again because that bears repeating. The data from the coronagraphs are consistent with 100% of the corona being structured in time. They're not inconsistent with other pictures, but they're consistent with that. That's really strange and exciting. Imagine if we could locate each of these in 3D. Moving out, you want to see what CIRs do. Here's a movie of a CIR seen from the ecliptic plane. If you could locate this front in 3D, you'd learn some things about how the solar wind works. And there's this movie that you've seen before. We know why we want to see when we're getting head faked. The last thing I really want to pull up here is we'd like to be able to measure three-dimensional substructures of CMEs and other features in the heliosphere. And people have been trying to do this for years. It turns out that the limit has been the noise level in existing data. And so Kurt de Koning and I last year did an analysis of a particularly well-presented Core 2 CME. We used some new and advanced noise suppression techniques, and we were able to show that it had right-hand chirality and verify that later it hit ACE. And the way to read this is, here's the image from Core 2. These areas are where we projected in 3D. This is an oblique view. This is a perspective view from SOHO's perspective. What I want you to see is that the core here lines up with the bright core feature in the SOHO image. So we got it right. And then also we measured the chirality and we verified that with ACE. All of these things require global, continuous, low noise imaging. And so we proposed Punch. This is my conclusion slide. We're going to do all these things. It's really awesome. We have 3 small sats to do it with. Thank you. 4 small sats, excuse me.
Okay, we have time for 1 question, maybe 2. Yes, Spiro. Can you come to the microphone? Because nobody will be able to hear you without it.
So Craig, if you're looking at the plasma, right, then across the field, you only have cross-field conduction, so no doubt about it, you can have tremendous structure. But looking at the magnetic field, especially in open field region, magnetic field is bound to be more or less, shall we say, weakly varying, especially if it's low beta. So these structures that you're looking at right now, are they all plasma structure, or do you actually think the magnetic field low down?
So these images, I'm sorry, I'm just trying to go fast.
Yeah, go ahead.
These images are sensitive to density, so we're measuring density structure only, but we can use the morphology of the features we see to trace the magnetic field. So if we see a chiral structure in a CME, for example, we can determine the chirality of the flux rope, but we can't tell you which way it's going.
Never mind the CME. CME we know is all-structured. I'm talking about the open field. Suppose I'm looking at a polar coronal hole. What do you think the magnetic field looks like there?
Well, I think I think the features probably trace the field, but we can't tell you which direction it's going.
Okay, great. Thank you very much.
Thanks.
Okay, our next speaker is Friedrich Boger. Excellent, from NSO.
Okay, got it. Okay, thank you very much. I am representing Valentin today, who couldn't come, unfortunately. I am part of the DKIST project. I'm the instrument systems scientist for DKIST, and I hope that maybe we can, as a DKIST project, provide some information about the magnetic field. As being part of the solar wind question that was just asked. So before I go into that, I'm giving a short overview over DKIST. It's a 4-meter aperture telescope with an alt-az mount. And one of the unique features is that it's an off-axis telescope. That means that it doesn't have any spider or central obscuration. We have to stop down the field to 5 arc minutes, right from in the prime focus. But we have taken a lot of care to make it a low scattered light telescope. So we plan to wash, for example, the M1 regularly. It is a coronagraph. It was designed as such right from the start. And it's got a Leo stop and a limo coulter. So we're quite equipped to go right ahead and observe the corona, and we plan to do that daily, actually. So it's got integrated AO and provides high precision polarimetry. And we plan to deliver the data via our data center in Boulder. Where are we at right now? Construction started 2010, and we have, well, as part of the design process, the actual site work began end of 2012. This is outlining the critical path, and as you can see, we've kind of come a far way, long way down to where we're at right now. At the end of 2018, we have integrated M1 and are taking images on stars to verify the optical quality of the telescope right now. Planned in the near future is the delivery of the wavefront correction system to the site and the install of that, and then rapidly come the instruments. So this is how it looks right now. As you might have noticed, the construction work is, at least for the outside of the telescope, has been done. Interesting here is the support facility over there. Here's a picture of the coated M1. And here's a picture of how it has been integrated into the telescope. Actually, this is not the blank, the Science M1. This is a test mirror that we procured to make sure that everything works out and the telescope's pointing in the right direction. When it comes to the instrument suite, we have 5 instruments, 4 of which are post-AO. The exception is the cryo-NIRSP, and I'll explain what that does in a minute. But I think it's worthwhile to point out that the focus of all the instrumentation is spectropolarimetry, and we have also taken care that most of the instruments can be fed in parallel, and the way that we do that is with a set of dichroic beam splitters that divert the light into different instruments at different wavelengths, and we can change these out so that we can change these bands into the different instruments. Again, the only exception is the cryo-NIRSP, which feeds off before it ever hits the adaptive optics system. So a little bit about the instruments themselves. We have the visible broadband imager. It's being built internally at NSO. It's a diffraction limited instrument and aims to provide high cadence and high spatial resolution images in the solar photosphere and chromosphere, as you can see from the diagnostics that I list here. It performs image reconstruction in real time so that the data for the image reconstruction process is reduced for export of the mountain. Then we have the visible spectropolarimeter. This is an instrument being built by the High Altitude Observatory, also located in Boulder. The VISP is unique in that it has 3 separate spectral bands, cameras for 3 separate bands. And that means that you can choose almost any combination of 3 lines and observe them strictly cotemporal. And the other very unique feature of this instrument is that you can tune it to go anywhere in the range of 380 through 900. So it actually stresses high spectral fidelity and flexibility, and will deliver high precision polarimetry. As the next instrument, we have the visible tunable filter. It's a imaging spectropolarimeter that has 2 narrowband channels that split the polarization states onto 2 different detectors, keeping the full field of view of the instrument, which is about 60 arc seconds. And then it has 1 broadband channel that is strictly cotemporal that will allow, together with the 2 narrowband channels, image reconstruction to get to the diffraction limit of the telescope as well. It scans through the different filters sequentially, so it cannot observe, for example, IN1 and H alpha at the same time, but it does that individually, and then it scans through the line as imaged here in this movie. So it will have very high spatial resolution and allow imaging spectropolarimetry, and actually very precise photometry. Again, this instrument samples the photosphere and the chromosphere. And now we get to the infrared instrumentation. We have 2 instruments. One is post-AO, which is the diffraction limited near-infrared spectropolarimeter. It can observe, similar to the VISP, 3 wavelengths, strictly cotemporal. And as you'll see, it has coronal, chromospheric, and photospheric diagnostics that you can tune the channels to observe simultaneously. It's a IFU-based instrument, so it gets you the spectral and the spatial information strictly at the same time, which makes this instrument very unique. So it provides simultaneous spatial and spectral coverage over a small to moderate field of views while maintaining high spatial resolution and spectral resolution. And last but not least, we have the cryogenic near-infrared spectropolarimeter. It also has multiple order sorting filters. It only has 1 spectral camera, but it has a simultaneous context imager channel. And it is a purely IR instrument, observing between 1 and 5 microns. It is also a polarimeter. So this instrument is particularly interesting to observe the solar corona, and we'll get to how that will contribute to the question of the wind and its chemical structure in a second. So before I go there, I want to again point out why we can do polarimetry pretty well from the ground in the infrared. Here's a picture of how the sun looks like at the beach on Maui and Wailea, and how much different that is on the mountain on Haleakala. So you can see that the scattered light is greatly reduced on the mountain. Now, if you look in the infrared, you can actually start to see the corona, and that is because the background of the sky is less than the signal of the sun. And that makes DKIST in the infrared very exciting for coronal observations. And again, we're planning to do these type of observations daily. Here's what you can see when observing the sun and from the ground. Actually, this is a picture from the ground. Oops, I'll do that again. Doesn't matter. So DKIST can observe the sun within 1.5 solar radii. After that, it becomes an issue to point the telescope further. But this is indicated by this red line. But this allows us to see loops like this, and so we're quite able to measure the magnetic field within this red area with, for example, the cryo-NIRSP and the DL-NIRSP. So how does that help in the context of missions like Solar Orbiter and Parker Solar Probe? Well, we can co-observe with these missions. For example, in this case, Solar Orbiter, here, this is the projection of all the orbits of Solar Orbiter onto the ecliptic, and here's the Earth, and here's the Sun in a static way, and one of the orbits is pointed out here. At this point in time, Solar Orbiter will be at a minimum latitude, and with the cryo-NIRSP, we can get in the ion 13 line a lot of context for the chemical structure or chemical composition of the solar wind. Similarly, when Solar Orbiter is in the ecliptic, we can again provide the magnetic field structure in the inner corona while measuring with Solar Orbiter the wind components perpendicular. And with Parker Solar Probe, similarly, we are able to co-observe to make sure that we can support by pre-measuring and when Parker Solar Probe encounters, and actually during the encounter we can measure magnetic field in ion 13. And we also get fields from Parker Solar Probe. Similarly, if we are interested in the chemical composition, we can do that as well with Parker Solar Probe, which allows us to model the heliosphere. Okay, so ultimately, right now we're in an area of multi-messenger information for solar physics, and so we're now actually able to measure particles, fields, and photons from the UV to radio with these missions. Okay, and that's it. Thank you.
Okay, we have time for one quick question. No? Okay. Well, we're going to take the time. Thank you very much, Friedrich.
Sorry.
Our next presentation is by Alessandra Passini. She's going to tell us about the new Arecibo Observatory Solar Heliospheric Program.
Thank you. Okay, this one. Hello, good morning. My name is Alessandra Passini. I'm here to present this new solar helio program, but it's not in a new facility as the KIST. I'm talking about Arecibo Observatory. So this is a 55 years old radio telescope that we have in the beautiful mountains in Arecibo in Puerto Rico. And it's a very well-known facility and have been developing and supporting sciences in three traditional fields, which is astronomy, planetary radar, and space and atmospheric sciences. Because we are not only a passive telescope, we are also a transmitter, so we do radar, planetary radar, and we do bouncings, and we use the capability to do incoherent scattering radar as well in the ionosphere. So this is a very well-known capability and also famous because of the big dish and in different movies along the years. So yesterday, actually, the team radar was there measuring the comet 46. So that was we are still, after 55 years of existence, we are still doing innovative science and having great results. So we are inside the SAS department, which is the Space and Atmospheric Science department. We have been doing and supporting science in aeronomy fields, so studying the ionosphere using the incoherent scattering radar, which give us lots of parameters about the densities, temperatures, and velocities of the ions and electrons from the bottom of the atmosphere up to the top side. But we also have a cluster of different instruments on site that support and complement the information given by the ISR that we have. So we have LiDARs, we have passive optics, and we have other antennas in radio. We also have the active experiments of the HF, so we promote changes in the ionosphere, and then we can measure these anomalies and how these structures are propagating in time and space. So for the helio community, I think the contributions that we were making up to now was basically in space weather, because we can connect topside, and then that's the most sensitive layer in the ionosphere to the plasmasphere, for example. So one example of that is this poster that we have on Wednesday showing a combination of ISR and LiDARs during different geomagnetic conditions. So this is very traditional in Arecibo, and we are doing a good job on that. But we went through a transition. I forgot to mention that Arecibo is an NSF facility, and we went through a transition at the beginning of the year through a new management team. So we are now part of the UCF and UMED team, NEA. And through this transition, I joined the team. And as a solar helio scientist, I started asking questions to my peers and also to the community about how can we use this facility to expand our knowledge about the helio problems and trying to study the solar corona and the solar wind up to the ionosphere, the bottom of the ionosphere. And the first thought that I have was, we can just repurpose the products of space weather and trying to place that in space weather and exoplanets, trying to help constraining models, for example, because we can get information about atmospheric escape and things like that can be helpful for the exoplanet community. And we are already doing that by joining projects from exoplanets scientists and new worlds kind of calls. But what was done up to this, what has been done up to now in the solar helio field? So I did a little research on that, and I saw that in the 70s and the early 90s, we were using, here and there, the capability to do passive solar observations and to also trying to do some active solar radar, which is trying to send out a signal, and then that can be bounced and scattered back by the solar corona. So it was done like in the 70s and then try again in the 2000s. Some work was done in trying to do interplanetary scintillation, which is not direct kind of measurements of the solar wind fluctuations. It was done in the 60s and 70s, and then it was also, one experiment was done in the early 90s. And by using the radar capability, we have one study using spectral broadening, because that also gives us some parameters and some information about solar wind. So that was all. And then, but by talking to the community in different conferences, I learned that many studies were, some campaigns were doing, or some experiments here and there, trying to, using and pointing the telescope to the sun and doing solar passive observations, but not more than that, those results were published. So what's my idea is trying to fully explore the capability and also open up the gates to this solar helio community. And by doing that, those are the receivers we have now. We went through the Hurricane Maria in 2017. So we lost one feed in 430 megahertz, which is used basically for incoherent scattering radar. But we still have another one in the Gregorian feed. And we got support from the NSF to build the new line feed, and also like to improve the alignment in the reflector, which will help us getting more gain in the higher frequencies, for example. So all these receivers, they cannot be used like simultaneously, because you need to rotate the floor and then change the frequency, but they have sub-bands inside each one of the channels, so you can do, you can use like, have some dynamic spectra inside one of the bands, for example. Besides the receivers we have in the big dish, we have also like other little receivers like VLF heliometer going lower frequencies, and we are having a new capability coming soon, which is called A40, which will be a phase array associated to the L band, and that will allows us to imaging, because now what we can do with our receiver, we can point to one source, but using the A40 will be a bigger, we will have a bigger field of view, and we will enhance the capability in 500%, so we will be able to electronically point the telescope to more than one source at the same time, which will be cool. So what do we start doing this year? So I joined the team in April, and I started studying and trying to figure what we could do. The first step was trying to reproduce and get new measurements from the interplanetary scintillations. So this is a great technique. So what do? You point your telescope to a very compact radio source that needs to be very close to the sun, so in elongation. And what you measure on the scintillation, the fluctuations on your signal are related to the fluctuations of the solar wind. So, which is very cool, and these, usually these kind of measurements are made in 327 megahertz, for example, and then you are probing scale sizes like from 10 to 1,000 kilometers in the solar wind, and you can, by doing that, you can point sources on the ecliptic, but you can also out of ecliptic, so which allows you to probe the turbulence in the solar wind out of the eclipse and ecliptic in different latitudes, heliolatitudes. So what we did in June we started trying to measure that and extract the parameters and get this information. But the first campaign was made in August after the SHINE meeting, and we had the support from the Dr. Manohara, who is the head of the Woody telescope, and he's been doing that for more than 30 years. And he was happy to come because our facility has multi-frequency, and we can go higher in frequency, which means that you are going closer to the sun and probing smaller scales fluctuations. So he was very excited to see what we could do with that. And I got the support from my colleagues from different areas in the Arecibo. So Shika, she's the head of the LiDAR lab, but she was excited to combine this information with the SAS thing, and we got Phil is supporting the astronomy group. So this effort, bringing the solar helio measurements, is really like promoting synergy inside the Arecibo groups, but also with the external community. So what we got here, we are now like preparing the first paper to report the measurements, the experiment, and the results. But here I just want to show you how beautiful is our spectrum. So because of course we have a gigantic collecting area, so we don't need to integrate too much the data and to get one beautiful spectra like that. So only 3 minutes on, 3 minutes off, we already get information from the Fresnel to the inner scales. And I'm here showing you, this is my favorite quasar that we were observing. And we were going very close to the sun. When I say very close, I'm talking about lower than 5 solar radii. So this is L band. I'm 1.6 gigahertz. So I'm going very close to the sun, and every day I'm reaching lower elongations, angles. And I still can see, of course, you are flattening the spectra along the days, but you still can see the inner scales, and you can see the Fresnel, which is very powerful to give you information about the velocities of these structures in the solar wind. And here I'm showing just one day that we did multiple frequencies, the same source. So we went from 327 up to C band. So here I'm showing what I'm showing, L band and C band, so from 1 gigahertz to 4 gigahertz. And as I told you, inside one receiver, I can have 7 sub-bands, for example, and already get 2 different frequencies in the same band. So by doing that, using a single dish, I can already extract the speeds of those structures in the plasma, in the solar wind. So it is very powerful as well. And that was the first time. I told you, like, we had 4 papers on that in the past, in the 70s and 90s, but that's the first time we are doing that by using the Gregorian feed we had, which is a better optics to concentrate the light to one point, so you correct the spherical aberration, so that's very cool. That enhances your gain. Okay, so near future, of course, Arecibo will never be a dedicated instrument for sun because we have other areas going on there, and we are supporting nanograv and new things in observing pulsars and aeronomy, but also because the sun is only in our being from March to September because we have this declination range limitation. So what we are doing now for the first 2 quarters, we have already a new campaign coming in, and that will be the first one that we can probe source close to the Parker Solar Probe, because the last measurement, the Parker Solar Probe was not there yet, and it was not like close to us. But also, like, the community is receiving very well this effort. So by contacting Mario Bizzi and the other IPS people, we are start talking about hosting the next IPS workshop in Arecibo next year. So that would be very nice to integrate the community. The other next step will be trying to study the feasibility of using Arecibo for passive observations. So we have all these receivers, and we will be how can we be complementary to the other facilities and help filling the gap between the sun to the inner corona to the low ionosphere, basically. And the other possible action will be like evaluate the use of the active mode. So by studying again solar radar or trying to use the planetary capability to do broadening. That will be like later next year. So one thing that we are already doing inside this program is bringing one of the Callisto spectrometer to the island. So that will be part of the AOSOL program, but it will be installed in the UPR Mayagüez, which is a University of Puerto Rico, that will facilitate the participation of students, because we are in a small island, but the students have troubles to get to the observatory because we are very remote and they don't have like ways to go there. So by installing this instrument there, we will be able to have some information about type 2 and help support our space weather traditional science, but we can also like integrate and facilitate the training of these students. And so here are my conclusions. And as Nikki Fox said yesterday, it's a very exciting moment to be a heliophysicist because of all these space missions going there. But we also have great ground-based support. And I hope Arecibo can be one of the support science that we can have from the ground to understand better our nature and our heliophysics. Thank you.
If we have one quick question, we'll allow that. Otherwise, we'll move on. I think we'll go ahead and move on. Keep on time. So our next speaker. Thank you. Our next speaker is Robin Millen, speaking on big science on a small budget, innovative experiments for radiation belt science.
All right, thank you for the invitation to speak. I wanted to talk about suborbital and CubeSat missions that both do great science in their own right and also can be used to augment some of our larger missions. And I'm going to spend most of my time talking about a project we've been working on for about 10 years now called Barrel. And then if there's time, I'll talk about some future projects we have planned. Is there actually a pointer here? Oh, there it is. Okay. Let's see, it's not forwarding for me here.
Oh, here you go. Sorry.
It's okay. Okay. All right, so BARREL stands for Balloon Array for Radiation Belt Relativistic Electron Loss, and that's what it is. It's basically the idea is to put an array of balloons in the suborbital region, which maps to the radiation belts, in order to study the precipitation of very energetic particles coming into the atmosphere. And the project was designed to work with the Van Allen probes, which were launched in 2012 into the radiation belts. And the idea was to combine our measurements of what's coming into the atmosphere with measurements being made in situ on the spacecraft so that we could quantitatively test some of the ideas of wave-plasma interactions causing the scattering. There are a couple reasons for doing an array of balloons. One is that we increase our chances of having these kinds of magnetic conjunctions with the satellites, so we can do those kind of conjunctive studies. And in addition to that, we were interested in studying the spatial structure of precipitation at these energies. The colors you see down here, of course, are just the aurora and the visible, and we have beautiful movies and images of the aurora and how it evolves in space and time. But at these relativistic energies of hundreds of keV to MeV energies, we had basically no information on the spatial distribution other than some long-term statistical averages. So that was another goal of the mission. So a little science motivation, why study the radiation belts? This is a movie of data taken, it uses data from the Van Allen probes showing the variability of the radiation belts, which is really the main mystery, I would say, still in the radiation belt, is how do you accelerate particles to relativistic energies in timescales as short as minutes in some cases. This shows the nice structure of the radiation belts, the inner zone, and this was actually the discovery of a third radiation belt that Van Allen probes made early on in the mission. But what you should focus on here is really the waxing and the waning of the fluxes of electrons in the radiation belts. And this shows the same thing in a spectrogram form. So this is radial distance from Earth versus time. And you again see these big enhancements of radiation belt particles. This is 5 MeV and 2 MeV. But I want to draw your attention to also where the circles are here are a few examples of cases where the radiation belts just completely disappear. So we lose the radiation belts and then they're subsequently rebuilt after that. And really, Barrel was targeting where do those particles go, how many of them go into the atmosphere, and what's causing the scattering into the atmosphere. So how do you measure radiation belt particles from a balloon? You look at the X-rays produced as the electrons enter the atmosphere. They produce bremsstrahlung. And we're essentially using the atmosphere as part of our instrument here, converting the electrons, which make it down to an altitude of 60 or 70 kilometers at these altitudes, or at these energies, to X-rays, which penetrate to altitudes where you can put a balloon between 35 and 40 kilometers. This is just an example of an X-ray burst seen by Barrel in 2013. Another nice thing about balloons is they don't move very fast like LEO satellites do, so you can actually study this interesting temporal structure here because you're essentially a stationary platform. And we see this actually quite frequently. It's something we're still studying and don't really understand. So we wanted to do an array of balloons, and in order to maintain an array of maybe, let's say, 5 balloons during an Antarctic season, which is where you like to launch balloons in the polar regions, of a month and a half, required building 20 balloons. We wanted to do this in 2 years because the Van Allen probe's apogee would sample different magnetic local times in 2 subsequent years. So that required building 45 of these payloads, because also if you're launching balloons every day or so, or every other day, you don't have time to fix anything, so you have to bring spares with you. So we built 45 payloads. That requires making them pretty simple. So we had a single instrument, an X-ray instrument that's called a scintillator, to measure the X-rays between 20 keV and 10 MeV. The detector's in the center here. This is what the payloads look like. Building 45 payloads, we had done experiments where we built 5 before, but building 45 is a whole different level and really requires you to change the way that you approach building things. And so the design was simple. However, we still had to drill about 10,000 holes per campaign in these simple aluminum structures, and most of those holes were drilled by undergraduate students. So we couldn't afford to pay a machinist to do any of that. But we did work with a machinist to help us come up with ways that we could do that, have an army of undergraduates drilling holes, but doing it in a way that everything would actually fit when you tried to put it together. Also, the INT, integration and testing, we did everything at Dartmouth. A lot of these boxes were built at other institutions, our COI institutions, but everything was put together and tested at Dartmouth. Again, we had to come up with procedures for having 15 different people build a payload that met the kind of quality standards you expect of a science instrument, and having them all be basically the same. So as we're looking forward to constellation missions in the future, some of the lessons we learned hopefully can be transferred to other people. So this is just a video of if it'll play. Oh no. Can you make it play, do you think? Just a video of one of the launches, just to give you an idea what it's like to launch one of these balloons. These are hand launches, so a little smaller than the astrophysics balloons, but none of them have launched 45 of them. So, it's hand launched because there's 2 people holding the payload and releasing it. In order to get this array up there and maintained, we had to do a launch like this every 2 or 3 days. To achieve that, we used 2 different launch sites, one in the South African Antarctic Station and one at Halley Research Station. That allowed us to fill this whole region with balloons. The balloons only stay out, our average lifetime was about 12 days, so you're constantly replenishing the balloons in this area and then using the circulation of the winds around Antarctica to basically fill this whole region with balloons. So those are the trajectories just from 2014 to give you an idea of what they look like. So now I want to talk a little bit about a couple of the science results. This is just a couple highlights that I picked. So as I mentioned, one of our goals was to try and study the global spatial structure of precipitation, which really hadn't been done before at these energies. And to do that, we used multi-point measurements. And this is actually work led by Aaron Brenneman. The top here actually shows Van Allen probe's plasmaspheric His observation. So this is wave frequency versus time. If you integrate the power over this frequency range, that's the black curve down here is that integrated power. And then the red curve here shows the X-rays measured by a barrel balloon. So you can see a really strong correlation between the X-rays and the wave power. And moreover, when you look at the wave power being measured at the 2 Van Allen probe satellites, and then also there were 6 balloons up in the air. Aaron looked at a couple different events, but you see a strong coherence of this kind of modulation across all of the measurements. And he used all these measurements to put that scale at 6 hours of magnetic local time and about 3.5 L shells. So a huge region of the magnetosphere that's kind of pulsating together with the wave power and dumping particles into the atmosphere. So that was a surprising result for us, this coherence over such a large scale. And it also suggests that plasmaspheric His is an important loss process for electrons in the sort of hundreds of keV energy range. Prior to Barrow, there were also a lot of suggestions of the importance of electromagnetic ion cyclotron waves, a different kind of plasma wave, and there hadn't been a lot of actual evidence of these waves causing precipitation. This is an example from Barrow. The top shows here, this is energy versus time, and then the color bar is X-ray count rate. And then this is actually wave data from GOES 13 showing, and these are the ion cyclotron frequencies. Here's the helium frequency, and so these are helium band ion cyclotron waves here. And you see a strong correlation again between wave power and the precipitation. So that was actually really exciting. We were also able to do some quantitative analysis by comparing in detail the wave properties and particle distributions with what we were actually measuring coming into the atmosphere. And that's some of these papers down here. One of the things that really surprised us, though, we have this big array of balloons to study the spatial scale and structure of these things, but for this kind of event driven by this different plasma wave, unlike the plasmaspheric hiss, we actually, despite the fact that we were seeing waves across the whole magnetosphere in some cases over very large regions, we actually only saw precipitation in very localized regions. For all of the events that we studied, only a single balloon detected the event, suggesting that they were much smaller scale than we were expecting. So that kind of was a new question that was raised. So just to summarize the barrel campaign, so to date we've launched 57 science payloads. So I mentioned the 40 balloons launched in our first 2 main science campaigns. We had those spares left over, so we were able to go launch those in some smaller campaigns in Sweden in 2015 and 16. They're still sitting in our lab, and we're trying to get rid of them all. So every chance we get, we stick a payload on another balloon. So we actually just launched a balloon on Sunday, a couple days ago, in Antarctica on a NASA test flight. So we've tried to really coordinate. As I mentioned, this was really designed to work with Van Allen probes. We've also worked with the MMS team. And we had burst telecons with the Van Allen probes teams every day during our campaigns to decide what data should they downlink in burst mode and coordinate the observations. We've also worked with a lot of the CubeSat missions and other ground-based missions as well. So not just the multi-point missions of Barrow, but also combining it with all these other observations has really allowed us to do science we couldn't have otherwise. And there are a couple of sort of summary papers there if you're interested in learning more. So I did want to just, in the last few minutes I have, turn my attention to just a couple of upcoming experiments. I mentioned the balloon we just launched on Sunday. This is a picture of it. That is a new NASA technology called superpressure balloons, and we're targeting a 100-day flight. And so this will be kind of a world record-setting duration, and also will allow us to hopefully get measurements in the slot region between the inner and outer radiation belts. So that's why we're interested in that. We're also designing we have a proposal in for a new balloon experiment and a CubeSat that was just selected. The balloon experiment, as I mentioned, Beryl sampled the spatial scale of precipitation on these large scales, but we discovered some of these things are actually smaller than the sampling that we did. We do multi-point measurements. The scale is actually really important that you're going for. So booms will actually image within a kind of a single barrel balloon field of view. We'll make images down to 5-kilometer resolution to try and probe the smaller scales, which we haven't had a chance to do yet. And then a CubeSat that was recently selected. We still don't know a lot about the processes causing the scattering, and with a balloon you're doing a very indirect measurement looking at X-rays, so we really want to measure the pitch angle distribution of these particles. And we learned a lot about what waves are scattering the particles, and now we really want to go with the microphysics of those processes. So this is a CubeSat that will measure electrons between 100 eV and 2 MeV. And it's actually, the key here is the pitch angle measurements that we'll be doing on really rapid timescales of tens of milliseconds. Another important thing about this mission is that we're using S-band and the APL ground station. A lot of the CubeSat missions to date have been really telemetry limited, so we're trying to do better there. So just in summary, I think suborbital missions still really have a lot of targeted science that they can do. And also I'd like to see more missions that are working with our bigger missions to kind of augment the science. Barrel's a really good example of that. And finally, I think, this is our first attempt at a constellation of balloons, but, we're all interested. I think the next talk is about constellations of CubeSats as well. And I'll just leave my last slide up. If you want to do your own balloon project, please come to the Balloon Town Hall on Thursday at 12:30.
Thank you. We have time for a couple questions.
How do you recover? Do you recover all the balloons in the flight payload?
Nope. The question was, how do we recover the balloons? In Antarctica, it's really hard. We tried to cut them down in places that were recoverable if NSF had the resources to go pick them up with their twin otters and helicopters, but we only got 2 back from Antarctica. From the Sweden campaigns, we recovered all of them.
So A follow-on question
yeah.
about the 180-day balloon?
Or 100-day, yeah.
100-day balloon, is that gonna, you expect it to just circle the Antarctic?
Yeah, so you saw those trajectories. It's supposed to circle and hopefully eventually will spiral outwards, which is why we're hoping to get some slot region measurements. This is actually a test, it's called Pathfinder for the Gusto astrophysics mission, which is a large astrophysics mission which will go on a 100-day larger superpressure balloon. Our payloads were the right size for the balloon they were designing for this, and so they invited us to fly. Yeah,
I would
excited,
guess
yeah.
Earth science might also be interested in long-term.
Yeah, exactly. I think if these superpressure, I'd like to see more small balloons. I mean, the astrophysics program really focuses on these really huge payloads, but I think there's a lot, especially in our field in earth sciences, where you could do a lot with smaller payloads.
Thank you. Our next talk is by Jonathan Parham, Leveraging Commercial CubeSat Constellations for Science, a case study. Sway it back.
It's under center there.
Finger should be right there. Use this.
Thank you. I'm Jonathan Brent Parham, and I'm working here to present some work we've been doing at BU, leveraging some commercial constellations of CubeSats that are currently on orbit taking data. Just the first off, the big picture view of, I guess, covering this whole session, we have the sun side of things, emitting solar winds, and then that interaction with Earth. And that's a whole big complicated system, and how do you measure all this? How do you cover all of the different dimensions that you need to understand to actually predict the system? For here, we're going to focus mainly on the auroral region, or the closer to Earth side of things, using a constellation of LEO satellites. Trying to understand the field-aligned currents with the instruments that we're downloading right now, but hopefully expanding that to the future things. Our group at BU tends to like to think about networks. You know, how do you use cheap sensors, get the information from a lot of cheap sensors, and then convey that back to something useful and scientifically. We have worked with GNSS receiver networks, doing TSE measurements of the ionosphere, trying to understand that, and then this work, which focuses on that LEO satellite constellation. So, as you can see on this picture, small satellite constellation, there's a lot of satellites there. That's nearly 200 satellites that are currently on orbit that we are using. That's far more than, one or two satellites that are currently used to measure field line currents, and nearly twice as much as the Ampere project using the Iridium constellation, which has about 60 or 70 satellites. And what is that constellation? It's Planet Labs. Planet Labs Incorporated, it's a startup out of San Francisco. I met them last year at AGU because they were giving a presentation here about using their ground camera, or their camera data, for other science, like monitoring glaciers, weather, and that sort of thing. That piqued my interest. Well, it's a satellite, it's got a point, it's looking at places like Boston up here, trying to get high revisit rates, trying to get high spatial temporal resolution. They have to have attitude control, and with attitude control, they have to have something like a magnetometer. Well, in fact, they have quite a few different sensors they use. They have the magnetometers, they have GPS receivers, infrared horizon sensors, and photodiodes all over the spacecraft, just to understand the pointing. All of the data from those spacecraft get downloaded to the ground and stored for diagnostics. All of that data measures its near space environment. So with this work, we made a collaboration last spring and started downlinking all of the data from their 200 CubeSats that are on orbit. These CubeSats are in two polar orbits, mainly, that cross at 10 a.m. in the morning because they're trying to take Earth imaging data at the same local time every time these planes swoop over. And that means that on the night side, they're not really doing much. They're crossing over the auroral zone at like 9 and 11 p.m. local time and just logging their data, sending it to the ground, not doing anything with it. So what we did, well, we took the data, we correlated it with a big solar storm or geomagnetic event back in September of 2017, just because we didn't really know how well these magnetometers would be able to characterize the field line currents, because they're engineering grade magnetometers meant for attitude control, we wanted to have something big, something dynamic that we could be sure that was geophysical and not just small noise in the system. So we looked at this strong, one of the strongest storms of 2017, found a period of time where one was, the orbital plane was flying over Themis ground-based all-sky imager, the Gillam camera, in fact, just south of the Hudson Bay, and just picked several satellites that flew over that camera. That camera happened to be one of the few that had a clear sky so it could see the aurora, and tried to correlate and tried to figure out whether we were seeing anything that was associated with the aurora. For this talk, I'm picking 7 satellites that flew over about a 10-minute pass, each separated less than a minute apart. Now that's 7 of nearly 200, and they're constantly replenishing these satellites. In order to process the data, we had to go and pull the data out of their body coordinates of the satellite system, use their attitude knowledge, or quaternion, to fix it to an orbital state, and then map that back to something geophysically relevant, like a northeast down coordinate system. With that, we also fed it through an optimizer that fit for a gain and a bias, a full matrix on that L and C, so that we could actually correct for non-orthogonality of the sensor and any time-varying biases for whatever span we're fitting over. And just to prove to you how well that fits the data and gets the noise down, so that brings the standard deviation of the magnetometer measurements at low latitude, so something that's magnetically quiet because there aren't really field-aligned currents flying there, to about 200 nanotesla standard deviation, or whatever deviation you want to pick, actually. And that is on par with early Ampere data before Brian Anderson at Johns Hopkins started working and beating down the noise by understanding the spacecraft better. So that tells us that, even just simply fitting for those gains and biases, we can get down to something that's relevant for the big storms. And then we probably can get a lot better if we work with Planet to try to back out any other noise terms. Here's some of the raw data, unsmoothed, of all the satellites passing over. And as you can see, it's going over their arc. You saw those first 2 flip their magnetic field deflections from left to right. Then we see the other guys also dynamically change, but in a different order. Now, this is right after, this is basically during the recovery phase of the storm. So the aurora is really dynamic. Lots of things are happening. Usually when people are looking at satellite-based measurements flying over the aurora, they're using pretty quiet arcs to try to back out the currents the best they can, because they don't want to have messy data that's got that spatial temporal ambiguity. So here we can see, well, there definitely is a spatial temporal ambiguity if you usually use only one satellite, because all of these satellites basically see different things. But several of them do see the same thing. So if we pick out the first 2 satellites and then a few later in the pass, we see those first 2 satellites saw pretty much the same magnetic deflection structure, which is indicated by a downward going current right here, and an upward current here, and an upward current here. They pretty much have the same structure, and then several minutes later, so that's 2:51 mean time for that crossover the all-sky imager, which is that blob there, we see another pair that also see a similar downward current, sharp downward current. And that sharp downward current is further south, and it's a little different for both of those, and a different structure from before. But just to kind of recover what this is, it's data from satellites every minute, taking every 10 seconds. We can take up to 10 hertz, but we're seeing similar structures with this really high revisit rate satellite constellation. We can then back out and look. There's those first 2 satellites that we looked at. They have that up-down magnetic field, which maps to a current density over here on the right. We take that data from the magnetic deflections here, plot it as the bars on this plot, and then take the current density estimate, which is just using a simple mapping, one-dimensional mapping, based on the satellite velocity, and plot that as a color on the stripe of the orbital track through a kilogram. So this is time versus the latitude of the orbital track through the Gillam all-sky camera. As we can see, these, again, are very closely spaced together. Those first 2 see pretty much the same east-west deflection change. And then we plot those, and we look at all the other guys, and just plot the next 7 satellites, and they keep hitting. These are the other 2 satellites I showed you with the really sharp downward current. But we notice that between those two pairs of satellites, it's pretty quiescent comparatively. And then again, it gets quiet after those 2 satellites. So we're changing on the order of minutes here. And if you're just flying satellites, 2 satellites, you're never going to see all this structure. And again, this is a very dynamic time period, so it's not, a lot of stuff is happening, and if you were flying through here, you wouldn't be able to make much use of a single satellite's data. And just to show you what the future capability might be, so this is data pulled from all of the constellation. The blue are vectors, the magnetometer vectors. Here, it's taking at the 10 hertz data rate, which currently, when Planet operates at the 10 hertz data rate, they're actually pointing the spacecraft, so there's some attitude control jitter that you're seeing as waves. But in the future, we could maybe collaborate with them and get them to take at this data rate without doing anything else on the spacecraft over some time period of interest that we coordinate with the sensor. But as you can see, over a 2-hour span, it crosses 2 all-sky imagers, and you have just plaster that region with data points. But you still can't quite resolve substorm that just happened, even though you have 200 satellites flying over the same region. So that brings me to the conclusion of, well, Planet Lab has 2 orbital planes that are flying, so you're only sweeping across longitude, basically. Now, in the next 5 years or so, there's these commercial interests like SpaceX and OneWeb, and including Planet, that want to throw up thousands of more satellites. This is thousands. It's nearly doubling or tripling the current LEO satellite population. Each of these will be carrying their own attitude control system, their own network of sensors to do their mission, but they probably will behave quite like Planet, where they're actually taking the data down, storing it and logging it for debugging purposes. Well, if someone can go in right now and start collaborating with them, that's a network of sensors that you cannot build by your own. And that it's going up there for free. All you have to do is start that collaboration. So I would implore people to start working with these companies, start talking with them before they actually launch, and maybe we can kind of influence their magnetometer choice or whatever choice. And even though these sensors might be less capable than in any flagship mission from NASA, they're much, much more plentiful, guaranteed. And I'd like to end with a note that the work I just talked about is under review right now in JGR Space Physics, and hopefully will come out soon if you want more detail. So with that, I'd like to thank you.
We have time for a couple questions.
No.
Yeah, how did you make contact with these folks in the first place?
So I knew about Planet. I'm more of an engineer usually, and I knew about Planet, and I came here last year to talk about our CubeSat, which is a swarm that's flying through the road to do something similar. And I went to their talk that was aimed at basically people to use their camera data, and I went up to them afterwards and was like, hey, do you have a magnetometer? Hey, have you ever taken a picture of this or that? And just started there emailing back and forth.
And have you spoken to folks at SpaceX and such?
I have several friends that work there, and I've talked with them a little bit. But
okay. So this guy's your hookup, it sounds like?
Yeah, yeah, talk to me. Any more questions?
Do you envision persuading them to upgrade their sensors, or is it more just get higher cadence of data?
Right. Well, for Planet, they reiterate every time they launch a new satellite. Mm-hmm. So their first satellites weren't very good. Their later satellites that they just they launched a few last month, or probably more recently. They're like on every rocket that you see a CubeSat on. It probably has a Planet satellite. But I know they're upgrading some of the things like their GPS sensors and stuff. So I hear it depends on what the collaboration turns into.
Cool.
Thanks.
Thank you very much.
Our last speaker is Phil Erickson, and he'll talk about the current and future community integrative science and discovery using incoherent scatter radar techniques.
Okay. So this is the...
Yep.
All right. Hit the play. Yeah, right there. Okay, I'd really like to thank the conveners for inviting me to give this talk. I am really doing this on behalf of essentially the entire incoherent scatter radar community. So although I'm giving the talk, I have many collaborators who very graciously provided me material to talk about some ideas about what one can do with a technique that actually has a very long history. And that's good because it's well calibrated, but is by no means a done kind of technology, as in we now know the perfect technology and we're just going to make more of them. It turns out that there is a very large and vast design space for this very powerful thing, and I hope to show you a little bit about that. And also, since this is a community that may have some people who don't necessarily think about incoherent scatter radar all the time, introduce a little bit about its capabilities and talk about the vast numbers of things in the geospace system that we can look at in more detail, and that the science is frankly crying out to us saying, we need to do this. There are things happening that you have not resolved yet. So that's my goal. As usual, I'd like to thank NSF for supporting us to do this kind of work and provide these sort of things for the community. So first of all, let's just spend a moment or two talking about incoherent scatter or Thomson scatter radar. This was essentially postulated by J.J. Thomson when he had figured out in the early part of the 20th century that there was this thing called an electron. But in the late 1950s, it turns out that technology had advanced to the point where the teensy little electron, you could actually scatter a radio wave off it, or at least have one go by that would make it wiggle and turn into a little Hertzian dipole and re-radiate a signal. And you can actually see right over here the cross-section of an electron, which is 10 femtometers on a side if it were a hard target. So it's a teensy thing. But it turns out that if you have a sufficiently loud radio wave that you illuminate a plasma with, and you have a very sensitive receiver, and again, in the mid-20th century, receivers got sensitive enough, you can actually get very weak backscatter from that. And it turns out that that weak part is actually a challenge, but it's also an advantage. Because the electrons are the things being light and not very massive that are doing the scattering, but their behavior is modified by the presence of ions. And so suddenly you start to have a very, very capable probe of the thermal plasma, the stuff below an EV. For those of you who like to look up radiation belt work, we're way down here. We're in the thermal plasma. And that's what the signal looks like if you hook it up to an oscilloscope. Yeah, that's right. It's about 20 orders of magnitude down from what I illuminated with. But if you do the right things in signal processing, you can end up getting a very powerful remote probe of, in this case, the ionosphere above our heads, because these things are on the ground in this case. Because at the moment, at least, technology has not allowed me to put a 2 megawatt class transmitter on a spacecraft. Those of you who are working on that, let me know, please. I'd like to talk to you. But the nice thing about this is it's an extremely robust first principle physics theory going right back down to the cores of plasma physics that allows you to turn this into a very powerful remote sensing tool. So that's incoherent scatter for you. And it turns out that this is a partial list of all the things that you can sense about the remote plasma. The basics are you can figure out what the electron density and the plasma temperature in both electrons and ions are. And then you can start doing more things like the composition of the ions in the plasma you're talking about. A vector velocity if you measure in more than one direction. Since ions collide with the neutrals, for example, in the E region of the ionosphere, you can start figuring out things about the neutrals, like the winds, temperatures. And then you can get ever more esoteric. If you like to look at how fast the ions are colliding with the neutrals, you can do that. You can even do a very sensitive probe of the background magnetic field of the Earth by watching how the spectral shape changes. We mentioned Arecibo before. You can actually look at the fact that the hydrogen ions are not the same temperature as the oxygen ions, and so you can look at energetics in the plasma. This goes on and on and on, basically because as long as you can remotely sense these particular spectral shapes and relate them back to instability processes in the thermal plasma that we know very well from theory, you can, for example, take these ion acoustic peaks and by looking at that and that, you can tell what the electron and the ion temperature are, and then you can start to look at composition. So this is a really, really powerful technique with a long, nice history, and it's been very well calibrated. And the nice thing is, again, I mentioned it's very weak, which means that the scatter here doesn't care about the scatter here, so you get the full plasma profile right down to the point where you're hitting the noise floor of your instrument. And yes, it has a detectability challenge. The figure of merit is megawatt hectares because that electron is a tiny thing. And so if you're illuminating even a lot of them, it's hard. But the point is that that gives you full altitude profiles, including the thermal information as a function of altitude, which is something that's really, really difficult to get with almost any other technique. There's also a Langmuir mode resonance here, which gives you electron density, which in some cases gets to 0.01% accuracy. So you can look at very fine scale electron density. Okay, so that's the technical, landscape. This is a little movie from Crank-Heitzelman of the current ISR coverage of that, and I'll pay my dollar to Joe Grabowski later for this figure, which shows up a lot. But this is the very, very complicated interlocked geospace system where we've got ion and neutral effects that are all coupled. It's a low beta plasma, so it's very strongly organized by the magnetic field. And this is our current sensor coverage with these particular ground-based facilities. And so obviously we'd like to increase that because we've got a lot of complexity in here. Already, though, we know that there's a lot of good science that ends up getting done with this. So, for example, I'll give you a couple of examples. Here's one thing that's a frontier thing. I will just do that. Auroral arcs. It turns out that because of magnetic lensing, you get very small scale auroral structures, which then tell you something, for example, about the magnetospheric electric field and energy dynamics. This, for example, is a movie that Craig gave me of optical emissions, and that is the current technology of the radar beam up at ISCAT. And in this particular one, you can watch these structures coming through. This is the radar measuring them, and it turns out that you're under-resolving what's going on here, even at half a second cadence and maybe under a kilometer range. Question is, what's outside the radar beam right there? How does that affect the electrodynamic response to the particle inputs? Because that's conductivity, and conductivity is regulating the amount of energy in there. We already know we need significant improvements in spatial and temporal scale, altitude resolved plasma motion, and obviously greater spatial coverage to understand that. And by the way, if you think that's complicated, then you can watch this one, which gets even more interesting. So there's a lot of geophysics just buried in really being able to do our job a little bit better. So that's a very attractive science target, and it's intimately related to magnetosphere-ionosphere coupling. Here's another one. This is from my friend Juha Virinen. This, in fact, is the Langmuir mode resonance. It's a little hard to see on this screen, but if you look very carefully here, that is the electron density profile. It is not a textbook. That's actually being measured, again, with about 0.01% accuracy. And if you look, you can actually see little ripples going up and down this of electron density variations of 1% to a couple percent. This is space weather in action. We do not know the precise nature of where this variability is. This is the weather. Climate is the average. When you take off the average, you get the weather. These bright things, by the way, are the Arecibo heater coming on and off. But my point is that this tells you a lot about intimate ion-neutral energy exchange. What's driving that? We know things now from below, basically space weather from below are being driven, as well as stuff that comes from above. And in fact, in quiet times, it's probably the natural winds and other stuff from below that are actually driving a lot of that variability. Which spatial wavelengths are important? Which temporal wavelengths are important? Not everything gets through the filter of when gravity waves break, for example, as much as they should. We know that in times, in fact, it's also driven from above and below. So what's the relative variation of that? And how do the background conditions enhance or suppress the response to some of this energy variability input? This is a direct incoherent scatter measurement. This is essentially the plasma telling you what's going on, very fine scale. Here's another one that our group has done a lot of at Haystack. This, for example, is an integrated map. It was mentioned before. This is made from the GNSS network. This is total electron content. So this is integrating all the electrons in a column above the ground. This is mid-latitude. This is in the plasmasphere boundary layer. This is where cold, dense plasma overlaps hot, tenuous plasma. Anytime you get that, you get energy and momentum exchange. There are these very large structures that we know, in fact, if you map them out into the magnetic spheric plane, are signatures of the inner magnetosphere, basically density structuring, and things like plumes coming, which have been subjects of entire monographs now and things, because it turns out that plasma, by the way, also when it hits the front of the magnetopause has been shown to regulate the reconnection rate. It's basically a negative feedback to the energy that the solar wind is putting in. So by sensing, not just with an integrated technique, but by fusing it with this incoherent scatter technique, which means I get altitude profiles and I get to measure the mass flux quantitatively, that's about 10 to the 14th ions per centimeter per meter squared per second, and I know what the temperature is in there too. So I can start to look at the energetics. So this picture adds greatly to this already coupled picture, which is a whole system picture. You have to, because of the strong magnetic field coupling, you have to understand everything. So we need wide spatial coverage, in fact, to study these kinds of things and figure out what controls what when. One more, if you really like frontier plasma physics, this is a low beta plasma, which is very difficult to make in the laboratory, and you can actually, there are natural instabilities embedded all over the place. This is the Altair radar near incoherent scatter class near the equator, and all of these kinds of things that Dave Heisel made in this particular measurement are all instabilities. These are Rayleigh-Taylor instabilities, gradient drift instabilities, even temperature gradient instabilities sometimes in some cases. And this is a measurement of the background electron density that these things are embedded in, which regulate the dispersion relations, which mean that I can figure out what instabilities kick and what don't. This is fundamental plasma physics. Again, all accessible from a radar that's sensitive enough to look at the background thermal conditions when this stuff triggers. So lots of fundamental science that can be done and is interesting to multiple communities. Up to this point, we've had quite a bit of diversity in experimental hardware. The classic ISRs, which, for example, we run at Haystack, are large. You need power aperture products. So you need a good sensor, this is the antenna, and you need to illuminate it with a reasonably powerful wave. So we would basically take single antennas in the 50-meter class. We would combine it with high-power single transmitters, which were developed by the military for doing hard target work. That's moved to phased arrays, where you synthesize the same instrument with a whole bunch of little antennas, which now you just have a control problem because you have more of them, but you can end up getting to the same place, and then this one's mechanically steered and you can electronically steer this. So of all the things that this improves, I'm going to hammer on spatial coverage for the rest, for the examples I give you of that. There's a very advanced system being constructed in Europe called iSCAT 3D. There are basically some transmitter and receiver sites. It looks like that. You know, very, very futuristic. And this is a little movie from Craig Heinzelman of a typical experiment where you see each individual pulse coming out in a grid, and the little red is the pulse coming out. And eventually, when it gets done with this 5x5 grid, you get that. You basically get a volumetric cube of what the plasma is doing. And so all of those irregularities, all of that fine scale structuring are embedded in this cube. And then you can throw lots of things like machine learning, like adaptive analysis at that particular measurement. So having a very flexible system like that is a way that these ISR systems are going to evolve to not just be the things that we've done conventionally, but to go further. Because now you get to throw the power of computing at this particular information, especially if you retain these pulses information as they come back and don't average it down as much as we normally would. We get to ride the industrial technology curve. I heard a quote someone that said, "I did nothing today and still got paid." So for me, doing nothing means letting the commercial hardware people solve the problem for me. And they're doing that thanks to these little things in our pockets called cell phones, which have software radios in them. So the communication industry is solving a whole lot of problems for us. Software platforms, computers have gotten fast enough that we can generally RF capture this stuff and then do something with it in computers. Data network improvements go as the cube of time, so there are vast network improvements. And even the transmitters have gotten better because people are making very nice power transistors. And why would you care about power transistors? This is a bit of inside baseball. Let me show you. This little entertaining video, by the way, horrifies electrical engineers. That's a guy shorting the output of a kilowatt class transmitter with his screwdriver. The transistor survives. That was not possible until a little while ago. Why would I care? This is because if I can do that and deal with reflected power coming back, I can actually steer a phased array to lower altitudes or lower elevation angles. The coverage goes from this to this. These little maps, by the way, are timed to figuring out that the electron density is within 5% uncertainty. Blue is better, and you can see the vast scale of improvement in coverage by this nice thing that the communications industry has solved for us. Bit or signal processing. Your home router has something called MIMO, multiple in, multiple out. We can do that with these networks. If we separate the transmitter and receiver, we can have multiple transmitters and multiple receivers, and this thing called combinatorics starts to show up. Again, many things, but I'm going to concentrate on spatial coverage. And by the way, there's your receive arrays. Turn the transmitter off, and they're multidisciplinary. So those of you who like to do radio astronomy, those of you who like to do solar radio, type 2, type 3 bursts, you can do that with those receive arrays at the same time, in fact, sometimes that you're transmitting. So for example, this is the last thing I've got here. We've got, this for example, is a map with only one site. So there's a transmitter and receiver right there. And again, blue is good, red is a little slower of statistical performance. If I put out 3 receivers now with a single transmitter site, well, then I get that kind of spatial coverage. And then if I put 3 transmitters out, I get that spatial coverage. Suddenly the measurement gets down to sub-second accuracy over a much wider field of view by basically throwing a lot of computers at it. So this leads to full geospace radar. This is an SH session, for example, and though you can actually turn the crank up and actually do scattering off of CME plasma. You can listen to type 2 and type 3 radio bursts and figure out what's going on in the corona. You can do this instability work. And my friends, for example, in Norway have done this to do actually lunar regolith measurements. They've used 6-meter transmissions to actually penetrate into the lunar surface with the same system. So this little tiny thing right here is all the things that you can do with this particular technique. So we're definitely not done. And it's of general interest. So that's one of the reasons why we wanted to bring it up. So it's a very powerful tool. It's well calibrated. But we've started. We've begun the process. Technology advances allow greatly improved performance. Instruments are inherently multi-role as long as you do the information flow correctly. The design space is vast. There's something for everyone. So really, there's not one more advanced design. What we have to do is discuss with the community what the science needs are, and we can actually tailor our design space to fit that. So with that, I'm going to leave that. There's a bunch of us in the ISR community who were thinking about this, and we were discussing earlier this week, we're going to begin to collect ideas about these sorts of things. And so I think the future is bright for this technique, and we hope we can use it in an integrative way. Thanks. Yeah, that essentially the geospace environment is filled with, at the very lowest, weakest level, it's this thermal scatter that I talked about where you're scattering off the thermal plasma. But embedded in that are all sorts of other plasma wave instabilities, which are where the plasma is trying to get rid of its energy. Those are much brighter in terms of radar scatter. So if you're talking about a direct plasma measurement, the geospace radar tries to look at those. It then extends to indirect measurements, as in they're interacting with neutrals, so you can figure out what's going on with the neutrals. And if you then keep going out into the inner magnetosphere and beyond, there are actually irregularities embedded in the inner magnetosphere that have not really been studied that are accessible with radar techniques like this one. So the idea is that we keep expanding our applications, much like this cell phone in your pocket, which keeps expanding its applications on a base radio. So that's the idea, is to then try to do this as a more multi-scale facility right from the get-go. So that's kind of what I mean.
Tom?
Yeah, thank you. It was a very impressive appetite for measurements that ISR can do. I remember in the 90s there was sort of a flurry of enthusiasm for actually diagnosing the space-based distribution and being non-thermal features in it.
Yes.
Is that still, respectable things that can be done?
There's a lot of work happening at higher latitudes. Roger Varney, sitting over there at Poker Flat, has done parallel temperature one thing, perpendicular one temperature one thing, and beyond that point to where temperature doesn't honestly start to mean anything, where you start to get the full velocity distribution function. There's a lot of work going on in the theoretical space to deal with that, but yes. And then I think the other comment to that, Tom, is that we're trying to match that effort with other people who are putting different 3D thermal ion imagers on orbit, where they also are looking at the full 3D velocity distribution function and trying to connect those together, right, I mean, because obviously there are many times when one temperature doesn't do it. So yes, the theory allows you to do that with limitations.
Let's thank Phil and all the speakers today. And just also want to remind everyone, we have a poster session tomorrow afternoon where we have a lot of other ideas and innovations. You can talk to the presenters there. Thank you.